Hello students, in this video we'll consider geometric optics in the context of partial differential equations. Let's be given a light ray in the xy plane whose wavefront is a curve in the xy plane. Okay, so here's our situation. Here's the xy plane. Here's x and here's y. And here's the t-axis. And what's happening over here is I give you some initial profile of this light front, right? And I want to figure out how this light front moves over time, right? And so to do this, what we're going to do is the following. We're going to suppose that we can suppose that there's a function u of xy, such that the wavefront at time t is the level set of u. And that just means that the wavefront is just the set u of xy is equal to t. So at time t, u of xy equals t is going to classify the shape of the wavefront set. Okay, great. Now with this in mind, there's a couple considerations that actually happen. Let's let c of xy be the speed of propagation of the wave. Then we know two things in the model. Then the model tells us two things. Our model is going to tell us that number one, if I look at the square root of x prime of t squared plus y prime of t squared, that's the speed of the trajectory of one of the light waves, has to be equal to what? It has to be equal to c of x of t, y of t. Okay? And number two is that the tangent vector to the light curve, x prime of t, y prime of t, that's the tangent vector, has to be parallel to the gradient of the level set of the wavefront, right? Which is just the normal to the wavefront. Those are the two assumptions of geometric optics, okay? Now for us, we're going to make a further reduction. Let's do a further reduction in this. And our further reduction is we're going to assume it's c, and then we'll go to a constant, right? And of course, this is like just the speed of light. It's a constant. That's the assumption of the other assumptions of the model. And so now, of course, what do we want to do? So now what we're going to do is we're going to plug in the light curve into the level set. So now if I look at u of x of t, y of t, that's equal to t. And if we take a t derivative of this thing, what's going to happen over here? If we take a t derivative of this thing, we're going to have ux by the chain rule, ux times x prime of t, plus uy times y prime of t is equal to 0, right? But good, but what is this? This is just a gradient of u, right? This is what? So this is just the gradient of u dot x prime, not equal to 0, but equal to 1, I'm sorry. It has to be a 1 over here. 1, okay? X prime, y prime. But of course, this is proportional, right? So in other words, this is equal to 1. But what do we know? We know that this is proportional. There's some proportionality constant, and this is going to be an x prime, y prime over here. So this is just going to be gradient of u dot gradient of u. So in other words, we have that gradient. And on the other hand, it's going to be also equal to what? It's also going to be equal to the speed, right? So it's going to be the speed of this curve over here. So what we're going to have is we'll have c squared. So this will say c squared gradient u dot gradient u is equal to 1. And so of course what this looks like is this now says c squared times ux squared plus uy squared is equal to 1. And this equation over here is a very famous equation. It's called the Eikonal equation. And it's a fully nonlinear P to E, right? It's fully nonlinear. Nonetheless, it's fairly easy to solve. Let me show you how, okay? So what are our characteristics? Our characteristics for this are going to be what? Well, this, of course, is like my P, and that's my Q, right? So we have dP over what? Over negative fx minus p f of u is equal to dq over what? Negative fy minus q fu. But there's no y derivative of your function f. There's no u derivative of your function f in here. Those are both 0. So your characteristic equations say that dp over 0 is equal to dq over 0, which forces what? Which forces p and q to be constants, right? And moreover, they have to sum up to give me basically 1 over c squared, right? So that allows me to say that p and q are constants. P, q are constants. And this implies what? This implies that p is going to be 1 over c times cosine of theta for some theta, and q is going to be 1 over c sine of theta for some theta, because now p squared plus q squared is going to be cosine squared plus sine squared times 1 over c squared, and that satisfies the equation over here. That's great, because now what that tells me my characteristics. If your p and q are constant, that means your trajectories are just linear trajectories, right? So these trajectories, these characteristics are just lines, right? And moreover, we can write down what the solution has to look like. The solution, u of x and t over here, has to look like what? Has to look like just 1 over c cosine of theta x plus 1 over c sine theta y plus another offset of a constant a. There we have it. There's the solution of this equation over here. Beautiful. And that represents the what? That represents the equation of a plane, right? And so there was that planar set. So we're traveling along a cone, right? That's the assumption we're making over here, is that the tangent plane to these surfaces, what will it envelop? It's going to envelop a cone, right? And you can figure out what the aperture of that cone is. So the Monge cone over here is genuinely a cone, right? That's the whole cone for the whole surface. So this family, this tells me that I'm propagating along, these are the surfaces of propagation, these are level sets of the wavefront. So I get really good information about the geometric optic. Now, of course, when can we solve this? If, for example, the initial data happens to lie on that cone itself, you won't be able to solve the problem, because then the characteristics align with the what? The characteristics are going to align with the initial data, and you can't propagate that data. That's an example of what's known as time-like initial data. Whereas with space-like initial data, you're not on that Monge cone, and you can propagate along the cone. So that would be space-like data, not time-like data. And so we get, from this seemingly complex structure over here, we get a very clean geometric picture of how light propagation works and how the wavefront set of light moves according to this PDE. Thank you very much.